Hi everyone, welcome back to our channel once again. In the last couple of videos, what we studied was mostly the cases where capacitor was having enough time to completely charge or discharge. But this is the case where capacitor doesn't have enough time to completely charge nor have enough time to discharge completely. So this is one of the interesting cases we have studied till now. Moving ahead, so this video what we are going to simulate the RC circuit where the capacitor neither have enough time to completely charge nor enough time to discharge completely is in accordance with the lecture which we have already studied in depth. To know more about the theoretical concept related to this RC simulation, I would recommend you to walk through the video which is available in RC playlist series with title as RC circuit with pulse input part 5. The link to the video is given in the comment box below. So let's begin. So the case where the capacitor doesn't have enough time to completely charge or discharge is decided by the T on and the time period basically. So let's draw the capacitive circuit. So this is the, you can say, a voltage source, a pulse. Then we have a resistor R, and in series with it is the capacitor. Okay, connected. So this is the pulse input 0 to 9 volt and 1K capacitor and 1 microfarad, 1K resistor and the capacitor of 1 microfarads. Now, this is the equation I have written here. For this, you can refer to the part 5 of RC circuit series lecture. I have taken from there. This is the charging, first charging, then this is discharging, very first time discharge, then again next charging, and then followed by the next discharging of the capacitor. So in this case, as you can see from this, we can find out tau equals R into C, which is 1 milliseconds. The time constant for this RC circuit is 1 milliseconds. Now moving ahead, the T on, or you can say the pulse width, is 0.1 millisecond, and the time period is 0.2 milliseconds. So this is given data to us. Now, if you compare the time period and the T on, we can say that the T on is much lesser than the tau, and T minus T on, which, or you can say T minus pulse width, is also much lesser than the tau. So you can see the T on as well as T minus T on both are much lesser than the tau time constant. Therefore, the capacitor will neither fully charge nor completely discharge. So let's try to understand with the simulation of RC circuit in LT Spice, and then we'll try to analyze this at the same time. Okay. So let's launch the LT Spice and go to the file, and you can draw the circuit. If you haven't, so let's draw the circuit. You can draw this, you can refer the last video to draw the circuit. We have taken the same circuit throughout the last 3 videos. Now, let's assign the values. In the interest of time, I'm not drawing the circuit step by step. If you have any doubt, you can refer the last video and draw the circuit with a value of 1K and 1 microfarad capacitance value. Now, but we'll try to do the assignment of voltage here. So initial voltage we'll consider as 0 volt, and since it is a pulse with higher value of 9 volts, so put here 9. The delay will keep it as 0. The rise time 1 nanoseconds, or you can put 10 as well. The rise and fall time both put 1 nanosecond. T on, that is the important here, 0.1 milliseconds here, and T period as 0.2 milliseconds. So it will repeat every 0.2 milliseconds if it is periodic. The number of cycles, let's keep it as 50, and then click OK. Go to the run button. You can see the waveform here. So this is voltage across the capacitor. If I click here, now if you want to see it in better way, go to the window, put tile vertically. Now, to analyze it better, or let's put 11, click OK. So what we can observe here is the capacitor starts charging, reaches close to somewhere 1 volt. Okay, so what is the exact value? You can find out using the equation given discussed here. So this is the charging equation of the capacitor. So at 0.1 milliseconds, if you want to find out the voltage, you put value, you put here t equals 0.1, which will give you the value, which is equal to the point 0.8565. Now, so this value, which we get after first charging of very first time the charging of the capacitor is 0.8565. Now the capacitor has attained a value of 0.8565 in zero point 0.1 millisecond. What happens right after 0.1 millisecond is we are changing the supply voltage to 0 volt. Thereby, this will behave as a short circuit and capacitor will start discharging from in the direction opposite to the flow of current here. Okay. So now the capacitor will start discharging in this direction and thereby the voltage will decrease. Voltage across the capacitor will decrease. So how much it will decrease is again governed by this equation, right? You can use this equation. How much will it decrease in another 0.1 milliseconds? Actually, the time to discharge this capacitor, at least it requires 1 tau, right? Which is 1 millisecond. But how much time we are giving it to discharge is 0.1 millisecond. And that's why it will not completely discharge. So on the very first charge, it accumulated a value of almost 856 millivolts, but it will discharge only almost 1/10 of it, because we have 1/10 of the time to discharge the capacitor compared to the time constant of 1 millisecond. 1 millisecond divided by 10 is 0.1. Thereby it will discharge 1/10 of it approximately. It doesn't follow the linear variation because it is exponential graph, thereby it will discharge exponentially. So you can see that it will discharge to a value somewhere near here, and that value is one that value you can again find out using this equation, which is 0.7750. So the capacitor, the very first time the capacitor had charged up to a value of 0.8565. On the first discharge from 0.1 to 0.2, it goes down to 0.7750. It means whatever we accumulated the voltage, it discharges only a fraction of it, which is 0.7750 volt. Okay, so you can see that here 0.7750. Now from here the capacitor will again charge. So the charging of the capacitor will start from 0.7750 after 0.2 millisecond, right? This is the point when we have 0.2 milliseconds. If you want a better access view, you can right click and put here 0.1. Now, after the first discharge of the capacitor, again it will start charging and reach to a value somewhere near close to 1.5. So that value is 1.558. The second time charging of the capacitor. So that value is somewhere governed by this equation. So if you put t equals 0.3 in this equation, you will get the value for the charging of the capacitor in the curve. That will be somewhere near 1.558. Okay, and that is the start of the discharging from 0.3 milliseconds to 0.4 milliseconds. So what's happening, if you observe the graph properly, what you can see is at the beginning the charging of the capacitor is charging at some rate and discharging, again charging, discharging. Then you can see the gap between the rate of charging is reducing gradually, but rate of discharging is increasing. So what we can conclude is at the beginning the rate of charging is more. As the time progresses, the rate of discharging is increasing and the rate of charging is decreasing. There comes a time when the rate of charging of the capacitor equals the rate of discharging of the capacitor, and that is this ideal state of equilibrium. And when we get the voltage equal to 4.5. So how can you, so if we try to analyze the mathematically how the rate of charging and discharging is varying with the time, this is the first charging equation, very first time when the capacitor charges, and this is the equation governing the charging of capacitor from 0.2 to 0.3. That is the second time the capacitor charges. So if you want to check the rate at which the capacitor charges here and here for 0.0 to 0.1 and 0.2 to 0.3, it's simple. You just differentiate this equation. By differentiating this equation, you will be getting somewhere near 9 differentiation is 0 minus 9 into if you differentiate this, you will get somewhere near 1000 into 9, which is plus 9000 into e power minus 1000t. Let's consider for e power some x. Okay. Now similarly, if you differentiate this, 9 differentiation is 0 minus and minus minus plus. If you do this, you will be getting somewhere near 8225 into e power x. So you can see the value factor, rate of differentiation mathematically decreasing from 9000 to 8225 factor. Okay. Therefore, the rate of charging is decreasing with as the time progresses. But if you differentiate this and this, these are the two equations governing the first and second discharging of the capacitor. That in you can find out that rate of discharging is increasing. Rate of charging is more at the beginning, but rate of discharging is less. As the time progresses, rate of charging equals the rate of discharging, and the output of the capacitor at the capacitor settles down to a value equal to 4.5 in this case. But the question is, how do we find out the average value at this point? After a couple of milliseconds, what value we get at the end? To get that value, I have already explained this in the video lecture part 5, but if you want to see it, it is basically the voltage across the capacitor that can attain the maximum voltage the capacitor can have, multiplied by the T on, that is the on time of the capacitor, divided by the time constant, which is here 9 into T on is equal to 0.1 divided by 0.2, that will give us 4.5 ohm. So you can see here in the graph, the value which we are getting is 4.5 ohm after. So the settled value or the fixed value, which average value which we get after almost 4 milliseconds and so, is equal to 4.5 volts. So you can play with the on time and the time period of, and then input pulse basically, and find out how does the graph vary. And we can also find out the expected settled output value across the capacitor in every case. So let's now go back to the pulse here and try to change this 0.2 to 0.3. If you change it to 0.3, now you can see, click OK and run. We get some value something like this. Let's change the axis to analyze it in a better way. So make it 11 milliseconds. So here you can see the settled value is somewhere near 3 volts. So if you apply again the same formula, the average value, it is basically the T on divided by T. This is how you find the duty cycle as well, right? So T on is here 0.1 and time period is 0.3, and if you multiply this value by Vc, which will give us 3 volt, right? So this is how you can find out the average value to which the output across the capacitor will settle down after a couple of time constant. After 30 to 40 time constant, basically it's settling down to 3 volts. So that's all about this video. Hope you found this video interesting and insightful. Stay connected. Thank you.